But to begin with, I'm going to start with a very short presentation from myself, trying to raise some questions perhaps for the panel, and also discussing briefly the work we're doing in this area. So let me just change screens. So just as a quick introduction, so I'm Josie Hughes, and I'm also at EPFL, where I lead the Create Lab, which we just started just under 2 years ago. And I want to talk today about embodied intelligence and, more from a design perspective, our quest for introducing and extending the complexity of our robotic systems and also using embodied intelligence for controllability. And one goal that we're really trying to work on is how do we achieve complex robotic systems? Through how do we design and fabricate increasingly capable robots that can begin to show the dexterity, the capabilities that we might see in biological systems. And what I'm really interested in is picking up on some of the topics Cecilia talked on yesterday about this idea of ecological niche. How do we extend the capabilities of current robots from being able to operate in a very small niche environment with a small range of functionality to be able to move towards the capabilities of humans or even animals, where they can operate in these wide varieties of environments or ecologies amongst different other humans or different animals, and also show a wide range of functionality and also perform tasks which are previously unseen or cope with uncertainties in the task domain. So we're exploring through how design and development of robots, we can try and move from the current capabilities of robotic systems closer to humans. So I wanted to start by looking at some of the approaches we're taking at, but then looking at what are the fundamental limitations which are perhaps preventing us from reaching this goal. So one area we're looking at specifically in manipulation is how can we exploit compliance? So Ord really talked about how variable stiffness, or how stiffness is important and how compliance is important. So we're looking at how can we explore what is the role of compliance and manipulation. So to do this, we're looking at making hardware, so in this case, a bio-inspired hand, where we can tune or vary the compliance. So here we have a 20 degree of freedom hand, but we have modularity in the structure. So we could even potentially add 2 thumbs. We can vary the structure of the fingers, but we can also vary the stiffness and the compliance. At the joint level, at the skin level, this is missing the skin at the moment, and also when we put it on the robot at the wrist level. So we want to explore how does this compliance distributed in different areas of the hardware aid the task performance, the robustness, or other such properties. So you can see here, we've just got some simple demonstrations of the tunable compliance, the ability to blend poses and synergies. And next we're looking at how does this distributed compliance aid task performance. So this is very recent work by one of my PhD students, Kai Junger, who presented yesterday. A second area we're looking at is exploitation of structure. So we know stiffness is important, but how do we introduce variable or controllable stiffness into larger structures? And to do this, we're looking at architectured materials. And we looked at how can we create architectured materials where we have a large tunability of the stiffness properties. And we developed these structures, which we call trimmed helicoids, where we take and some helicoid structures and trim the inner material. And these give us some really interesting properties, as we try and illustrate on the right, because through control of the geometry, through the helicoid and the trimming, we can have independent control of the axial and bending stiffness. And this is really important to be able to tune and optimize not only the workspace of the robot and the compliance, but also sensitivity to noise in tendon length or tendon control. So this gives us a really interesting design space of structures and materials to be able to then add actuation and form robots. So to this end, we then add tendon-driven actuation to these architectured structures to form kind of elephant-inspired manipulators, as you can see here. And these robots these structures can use us to create these continuum-style manipulators, which give us a great degree of maneuverability and exploration, And we can also tune, so on the bottom here, we have on these x-axis of these plots, we have the ratio between the bendian and axial stiffness. And as you can see, we look at how these properties vary for this robot, the workspace, sensitivity or error, compliance, and workspace reachability. So this allows us to then explore these various trade-offs by tuning the geometrical parameters to find the optimal parameters for a given application. So for example, we can select geometry that allows us and provides the highest precision or rejection of errors in the controller. And we can also look at the compliance. So how can we tune or select a compliance that helps with task performance and even allows compliant interactions with humans? Another aspect we're looking at is how can we exploit materials and sensing? And with this specifically looking at underwater structures. So here we're looking at if we have this very simple squid-like robot, can we tune or optimize the material properties to be able to improve the cost of transport at the swimming speed? And what we find is just by changing the material properties, so having on this bottom optimized structure, having a stiffer tip and a stiffer root and a softer tip, we can improve the efficiency through co-optimization of the material and also this simple controller. And we can also inject or create sensors within these soft tentacles where we can do pose reconstruction. And using this, we're looking at using proprioceptive metrics to be able to online optimize the trajectory to optimize for cost of transport or swimming speed. The final example of embodiment I want to touch on, which is moving away a little bit from soft robots, is can we exploit environmental constraints? Can we exploit soft or somehow flexible points of contact with the environment? And an example might be, for example, in all these cases, biological systems or animals or even movie characters are exploiting these tethers or these contact points with the environments. Spiders would be another example. So can we have this idea of using these tethers to allow or to provide an embodied solution to allow robots to operate in extreme outdoor conditions such as this? So one specific use case we're looking at is in glaciers or in ice caves, such that we have around us locally. And we're looking at creating robots that are using these variable length tethers where we have a fixed reference point to the environment. And these offer us some very interesting properties, even though it's a very simple system, but we get improved energy efficiency, pose reconstruction, simplified control, and also we have this kind of embodied safety limits provided by the tether. And this allows us to explore very large scales and very extreme terrains. So this is some recent experiments that were undertaken, taking these robots to very harsh extreme terrains, where we were able to go over 25 meters deep into some glacial environments to capture LiDAR data to allow for understanding of these glacial environments. But if we look at all of these examples of where we try to introduce embodied intelligence into the design of our robots, if we compare them to a biological equivalent, we're far away from the capabilities that we see. And my question is this a fundamental limit? Is there a fundamental limit on the extent to which we can close the gap between current robots and human or animal capabilities? I think we can take, for want of a better word, conventional AI approaches, and this can close the gap somewhat. We can also improve technologies in terms of fabrication, material sensors, and this probably can also improve the capabilities somewhat. But still, I think we have this gap that remains. I don't think this is perhaps the entire answer. So is there something fundamental in how we approach the design of these robots that is limiting us? Is there something missing in our current approach? And I think one issue is this idea of replicating the final state of a robot. Can we instead learn from biological systems that we need a more developmental and growth-based approach to design of robots? And to this extent, do we perhaps need to explore learning and processing or even design on different temporal scales, rather than this all happening at a fixed clock rate or clock speed? Do we need to introduce more low-level physically regulated or stabilized processes, such that we have some amount of this more decentralized and offloaded? And can we also move to more developmental or growth-based design? And finally, I think to move to an area we have a wider environment and wider functionality space, we also need to think of what's a meaningful evaluation or fitness function. What are we trying to optimize for beyond a single task? And can we look to biology to understand again, what are meaningful fitness functions or objectives to try and achieve? So within this area, we're looking at a few kind of approaches to addressing some of these questions. So first of all, perhaps looking at online change of morphology to see how that can aid control. As I've already discussed, looking at tunable or online tunability of compliance, looking at the effect of growth and how growth affects our ability to learn and how can we couple growth and learning together. And also for creating meaningful tools for evaluating robots. So here we're creating what we call a soft sensorized physical twin to evaluate how a robot and a human can perform complex tasks, such as harvesting of a raspberry. So I just want to thank all my fantastic students who have really enabled this work. So thank you very much for listening. So that was my first introductory presentation. So we were going to continue this session with another 4 talks from our speakers before having a panel discussion at the end. So please do put any questions you might have for our speakers in the chat.